All right. So graphs can have values attached to them, or the edges in graphs can have values attached to them. And we call these weights because we don't necessarily know what they represent until we're talking about a particular example. In this example, these weights represent the distance in miles between two cities. So from Philadelphia to Pittsburgh, that's about 320. Pittsburgh to Cleveland is about 130. Cleveland to Toledo is about 120. And again, if you drive these distances, right, it of course takes 320 miles to get from Philadelphia to Pittsburgh, and then Pittsburgh would be 320 miles to get back. There's not like a different value to get back. Now, directed graphs. If we're dealing, so this is on directed graph. In directed graphs, you can totally have different values to go between two cities. Like when you're looking at flights, to fly from city A to B, that's one price, but from B to A, it's a completely different price entirely, right? Take a look at one-way prices, and you'll be surprised at the disparity. So we're going to talk about pathways now, specifically between vertices. We mentioned about paths. A vertex is adjacent to another vertex if there is an edge from it to another one, right? So Philadelphia and Pittsburgh are adjacent. I mean, yes, not really. They're 320 freaking miles between them. But on this graph, they're adjacent, right? That they're adjacent on the graph, right? The graph only models only what it gets. Okay. In this example, Indianapolis is adjacent to Columbus, and Indianapolis would also be adjacent to Fort Wayne and also to Chicago, right? Philadelphia is not adjacent to Chicago. They are a very long way away. I know because I have driven that path a couple times. So when it comes to directed graphs, A is adjacent to D, but D is not adjacent to A because we can get from D, so if we can go from D to A, so they're adjacent, but A is not adjacent to D. So paths are basically, well, they're kind of self-explanatory in that name. You can kind of figure it out. But that means that there's a way we can connect the edges to one adjacent edges from one to another to get to our final destination, right? So there's a path from Philadelphia to Chicago, right? If we go from Philadelphia to Pittsburgh, then Pittsburgh to Columbus, and then Columbus to Indianapolis, and then Indianapolis to Chicago, that's a path there. There's also another path this way. If we go from Philadelphia to Pittsburgh to Cleveland to Toledo to Ann Arbor and to Chicago, right? Right, so so now to answer a burning question that I'm sure many of you are having now, what about like repeats, like if we were to go from Philadelphia to Pittsburgh to Columbus, then to Cleveland, then to Toledo, and back to Columbus, and then to Indianapolis, right? What about that? Well, a lot of times what we care about are simple paths, where basically the first and last vertices are the only things that can possibly be the same. So, for instance, if we were doing like a grand tour or something. But here, in a simple path, everything is distinct, right? Philadelphia, Pittsburgh, Columbus, Indianapolis, Chicago are all distinct, right? That's a simple path. This is not a simple path. So the other thing is cycles. A cycle is a simple path where the first and final vertices are the same. So Pittsburgh, Columbus, Toledo, Cleveland, Pittsburgh. This is a cycle. Where does it start? In this graph, right, it starts in any of these locations. You need to have 3 vertices to be a cycle, right? We don't consider Philadelphia and Pittsburgh by itself enough to be a cycle. So if it has a cycle, then we consider it a cyclic graph. If it has no cycles in it, which is way more common for directed graphs, we get an acyclic graph, something that we'll tackle later when we get to directed acyclic graphs. So finally, a graph is connected if there's a path from any vertice from every vertice to every other vertice, right? Here in this graph, we can start at any vertice and travel to any other vertice, right? We can consider all of the mainland United States to be a connected graph, or rather all the major cities in the mainland United States to be a connected graph. However, once we throw something like Hawaii into the mix, well, then that's not a connected graph in terms of like driving, right? There's no path to get for me to drive from Philadelphia to Hawaii. And although I will admit, when I was 4, I always wondered why there wasn't just a bridge from California to Hawaii. It seemed to make sense to me when I was 4, right? So again, this is a connected graph. But once we remove this relationship between 4 and 6, we have made this we've made this an unconnected graph. Okay, now although it's an unconnected graph, we have connected components. We can kind of look at this 4 or 5 and as a mini small graph, and 6, 7, 8, 9 as its own mini small graph. But the entirety of the graph is not connected. Oh, yeah, and if 4 is just its own thing, right? It's connected. It's a connected component with itself, right? So finally, the relationship between a tree and a graph. A tree is actually just a special case of a graph. Any graph that is connected, that has no cycles, then we can turn that into a tree by just kind of grabbing one of the vertices, like D over here, and just making it the root, dragging it to the top, and sort of letting everything dangle off of it, right? And that's how we can look at any of these graphs with a tree.